Hello, everyone, and thank you for joining. Thank you, Pose, for accepting yet again our request for delivering this talk. Thank you very much for your time, and please start.
Okay. Hello, everyone. So welcome for today's talk about universal algebra. And I think to actually start talking about universal algebra and put everything into perspective, a very good starting point is this talk by Stephen Banach. So Banach said that a mathematician, as you can read in the screen, is someone who can find analogies between theorems. That's more or less what everyone can do. But a better mathematician is someone who can even think of analogies between the proofs of those theorems. But the ultimate or the best mathematician is someone who finds analogies between theories. And today's talk is, in this sense, a very Banachian because this universal algebra is all about finding analogies between algebraic theories, algebraic ones, right? So this is what we mean more or less when we say universal algebra. Um, okay. So maybe to start from common ground, let's start with something everyone know through their undergraduate years. So we start with studying like symmetries of geometric shapes like triangles or squares or so on. And we come up with various groups. So the dihedral groups, the symmetric group, and very quickly we realize that we can axiomatize this structure into the notion of a group. And we define a group as some set equipped with a product with some kind of an inverse operation and an identity satisfying a list of axioms. And maybe, just maybe, you might be wondering why I'm adding this inverse and I'm adding this identity as part of the data I have to provide. Whereas in practice, we usually say there exists an inverse, there exists an identity, and I hope by the end of this talk, you will understand why and why making this into a part of the structure is actually very important. And it is very essential for everything going on in universal algebra. Okay, next we start thinking about numbers. So we see integers, we see real numbers, we can add and multiply them. We do the same with matrices. Some of us learn about modular arithmetic, and out of nowhere, we come up with the axioms of ring theory. Actually, not out of nowhere. It is precisely coming from these examples. But the whole point is, again, we axiomatize this as a set equipped with some operations, so in this case, addition and multiplication, and some distinguished elements satisfying a list of axioms. And now I would like actually to go back to you and ask you, which other algebraic structures have you seen as an audience? So what I would love at this moment is maybe someone unmute themselves, or write in the chat what kind of other algebraic structures have you seen? I would like to hear from you. Any volunteer? Okay, I hear ideal. Good. What else? Field, very nice. Groups. But rings and modules are already, and groups are already mentioned. So modules maybe? New, a suggestion? Any other suggestions? Final call? Final chance? Okay. Okay, algebras. Wow, nice. Uh, I see. Algebras, okay, it's the same as K algebras. Nice. Lie algebras, okay, now we are getting more interesting stuff. Okay. Any other? Vector space. Wow. I love this, you guys. I love you really. You are bringing all the examples I really want to talk about. Operator algebras. Oh, now, okay, now it is getting crazy, I guess. Uh-huh. Anything else? Monoids, quantum groups. Oh, now it is going beyond my control, actually. Quantum groups. Okay, I think that's fine. I think we already did a lot of examples. So, okay. So I'm really happy with these examples because universal algebra very, very easily covers everything here and covers Lie algebras, cover vector spaces, cover monoids. Whether it cover like operator algebras and the quantum groups, I wouldn't say so. And I will talk about this near the end because, of course, universal algebra is not after all that universal. It has its own limitations at the end of the day. And I will talk about these limitations near the end. But it is very good idea to actually keep these into mind. And if I forget, please remind me to discuss them at the end. But in any case, in an undergraduate ideal education, one should see some Lie algebra, which was already mentioned. Boolean algebras was never mentioned. I actually expected them. Some of us might have seen lattice theory. Some people really interested in logic will see something called forensic algebras. Vector spaces, of course, are very common. Modules are so. Some other less common algebraic structures are MV algebras, semigroups, heaps, quasi-groups. And if you are interested in some homotopy theory, maybe you have heard of DG algebras. But I have also pointed this as red because it is at the edge of what universal algebra cannot do. Okay, but the whole point is universal algebra encompasses all of these examples into one uniform framework. So you see, it has a crazy wide range of applications, and that's nice. Okay, so the way I like to think about this, and maybe this is a bit philosophical, is here is our Platonic world of examples of mathematics, right? And we start classifying those examples with first maybe I should Platonic world of algebraic structures, not all of mathematics, because geometry is definitely not here. But in any case, we have this world, and we start classifying these into some kind of theories. So with these examples here, we get into ring theory. With these examples, we get group theory. With these examples, we get Lie algebras, and so on. And I would like to think of this as a first level of abstractions from the Platonic reality into some abstract theory, right? This is a bit philosophical, but the point I am trying to sell to you is once you go one step in this abstraction ladder, you have to climb it all along. So this is maybe where most of us are used to. Universal algebra comes as a second or a further step, but it is not the only one. That's why you see these dots here, because we can go up even more in this abstraction ladder. But today I will just, take you one step further. That's hopefully the aim. Okay, so I told you that universal algebra is all about analogies in algebraic structures. So maybe a good starting point is to actually talk about these analogies. So here what I did is I listed some algebraic structures that I hope it's familiar to most of you. So groups, finite groups, abelian groups, rings, Boolean algebras, fields, Lie algebras, and vector spaces. And here I have listed some of the properties that we might compare these algebraic structures by. So for example, here I ask what kind of object we use when we take a quotient in this world. So for example, in a group, we take a quotient by a normal subgroup, right? In a ring, we take a quotient by a two-sided ideal. In Lie algebras, maybe I forgot to write this, we also do this by what sometimes is called the Lie ideal, but it is more or less an ideal. Here, for example, in vector spaces, we use vector subspaces. And here are some further, information. So for example, whether this is stable under quotient, yes means yes and no means no. So this is yes, for example, because a quotient of a group by a normal subgroup is a group. So everything here is yes, as it's clear. But for example, when we go to the product, and here I don't mean a product of two objects. I mean arbitrary product, right?
Fawzi,
So yes.
just could you clarify what do you mean by stable?
Yes, I mean that when you take the quotient, you remain inside the same algebraic structure. For example, when I take a quotient of a group, so when I take a quotient of something of this kind, by something of this kind, I'm still something of this kind. So if I take a quotient of a group by a normal subgroup, it is still a group. When I take a quotient of a ring by a two-sided ideal, I'm still a ring. When I take a quotient of a Boolean algebra by an ideal, sorry, it is a Boolean algebra. When I take the quotient of a Lie algebra by a Lie ideal, it is still a Lie algebra, and so on and so forth.
Oh, okay,
Um,
thank you. Thank you.
yeah. And next is the product, and that's where something more interesting happens. So here, for example, if we take a product of two fields, it is not a field, right? And maybe you know this. And as I said, when I talk about product, I mean arbitrary products. So, for example, if I take an arbitrary product of finite groups, I get an infinite group. So, for example, when I take v mod 2 multiplied with itself infinitely many times, I get something infinite. So I go very quickly outside of finite groups by just taking products. That's why I make a cross here. I have a first isomorphism theorem, and this holds almost everywhere. Maybe I should also actually be careful about some of the texts here, because this depends on whether I regard the zero ring as a field or not. But this is more of a technicality. Most people don't view the zero ring as a field. And if this is the case, then this will actually be across, will be across. But it is more of a convention, so let's pretend it is okay. Okay, and the final thing is a free object. Of course, I don't assume you to know what is a free object, and actually what one aim of this talk is to tell you what is a free object and give you a general construction of it. But at least you should know what is a polynomial ring, and I tell you from now that this is a polynomial ring. This polynomial ring is a free object inside rings. In Boolean algebras, this goes under the name of Lindenbaum-Tarski algebra, especially for people doing logic. For other algebraic structures, we don't have a free field, we don't have a free finite group. So you see from this like data set, we have some interesting similarities. For example, this column here is very, very similar to this column here. It's very, very similar to this column here. It's very, very similar to this column and this column. They are more or less have very similar properties, right? And these are how many columns? One, two, three, four, five. Five columns. And there is this, philosophical rule of three. When something repeats three times, or when you see the same pattern three times, you should abstract this away. Think of it like more of a code, like a code you write in Python or something. If you have to copy the same code three times or more, maybe it is the right time to create a function or a method and put the code there and just recall it whenever you need it. For example, when we talk about the first isomorphism theorem, we have to prove it. You see how many times, every time you have an algebraic structure, you have to prove this again and again and again, maybe 4 or 5 times. And of course, this is not economic. And therefore, we have to come up with a machinery or a framework where you can prove this theorem once and for all and just use it until the end of time, right? But also we would like to explain the differences of behavior. For example, why don't we have an infinite product of a finite group is a finite group? Of course, we can see an example, but philosophically, what is the reason? What is the deeper reason? Why a product of two fields is not a field? What is happening? Where is this weird behavior coming from? And universal algebra will, and I will today explain you why this is the case. You will, by the end of this talk, I promise you will have, oh, and now I see why a product of two fields is not a field. Where this is coming from, it has to do with how the axioms of a field are structured. And the same for finite groups. So the answer, just to, to kill the suspense, is that these theories, these algebraic theories, are not equational. And the good ones are equational. Of course, I will explain to you all of this, but just to prepare the stage a little bit. Okay, so maybe one final um, uh, motivational thing before I actually go to the details is that universal algebra is all about the study of general algebraic theories. And as I said, has to do with the economy of thought. We don't want to repeat the proofs all over again. And it also gives us a methodology to explain the analogies and differences between these algebraic theories. And it is not just about this, but actually it has a lot of applications. So one very important application is in logic and precisely algebraic logic. And personally, this is how I got introduced to this circle of ideas. In many years ago, I was insanely interested in algebraic logic, and that's where I got to know about this universal algebra. But recently, I got to know about some applications in number theory. So in number theory, there is this construction called Witt vectors, which are like an infinite vectors. So it is something like this. So x0, x1, x2, right? But these xi's are coming from positive characteristic rings or something. And in any case, these Witt vectors are very important in number theory because they allow you to go from characteristic P to characteristic 0, which is very hard. Usually, it is easier to go from characteristic 0 to characteristic P, right? But go back is quite hard. And these Witt vectors are one of the very few ways we know how to go back, right? But the problem with Witt vectors is, because this is a very hard process, if you try to write down it explicitly, it is a horrible thing. You know, I always make the joke because you have to write down a lot of formulas, a lot of equations, a lot of calculations, and they are quite involved. And I always make the joke that I have learned the details of Witt vectors 5 times, all the details. I work throughout all the details, and every time I go through the details, I feel like I understand it less because it's too complicated. Every time I get more confused, right? But the amazing thing is, with the machinery of universal algebra, everything is explained. I can prove that these Witt vectors exist. I can prove a lot of their properties without writing down any formula. So actually, maybe you write a formula, but it is like, a baby formula, a very easy formula, and everything follows from this. Whereas for the original approach, it is insanely formula driven. I promise you, it is insane. So this is, I think, is a very nice application, but also it doesn't end there. Universal algebra gives rise to a very interesting mathematics. So you have so-called Liouville theories in category theory, and this in itself gives rise to what is called animation. Maybe the correct word here is actually not topology, but maybe I don't know. Maybe one can write here derived algebraic geometry, or maybe homotopy theory or something like this. But in any case, these operations are very important in their own, and they are now being used a lot in research. Okay, so you see, universal algebra is also useful in applications. Okay, now we start some mathematics, but maybe before I actually start doing the math, I would like to stop and ask if you have any questions until this point. Okay, does anyone have a question?
I think no one. I cannot see any in chat.
Okay,
Yeah.
good. Okay, this means either everything is clear or I'm talking to the wall. Okay. In any case, I hope it is the first one. So the common framework of universal algebra starts with this notion of an algebraic structure, or what is usually called an algebra. And since I have heard the word algebra when you recommended some or give an example of algebraic structure that you know, this usage of the word algebra is different, right? So just have a fresh mind of what an algebra means. So algebra in this universal setting, it just means a set equipped with some operations on this set. And so let me maybe explain what is an operation. So usually we have so-called an n-array operation, which means a map from the Cartesian product of n copies of the set A into A. So for example, you can have something like a binary operation. So this will be a two-array operation. So it will be a map from A times A to A. You can have a three-array operation. So it will be a map from A cross A into A, and so on. So the number of these components we call the arity of the operation, right? So this is the arity here, the n. And as an example, which is you can view maybe as a convention, a zero array operation, which should mean a map from A to power zero to A. But A to power zero, you should think of this as a point, a singleton, a set with one point. You can view this either as a convention, or it's actually not a convention. It is more of a degenerate case of what it means to take the product. But if you don't see this, maybe you take it as a convention. And therefore, a zero array operation is just a map from a singleton to a set A. And therefore, let's call this map E tilde. And this E tilde is totally determined by its image on the point, and therefore this is just an element of A. So said otherwise, a zero array operation is just an element of A. So for example, in a vector space, we say zero is a distinguished element, and we can just view zero as a zero array operation. Why I am bringing this up? Because I want to include everything as an operation on a subset. So when I have a distinguished element, to view it as an operation on A, I view it as a zero array operation. That's the whole point. Because algebra, so this is the word algebra, or an algebraic structure informally, is just a set with some operations on it. And I want to include everything as an operation. So I'm just starting by saying elements, fixed elements or distinguished elements, can be viewed as such operations. This is everything I want to say. And then, so again, so algebra, I will use this word to mean a set equipped with some set of operations. And when we have an algebra, we can always think of its signature. And this means what are the operations? So I just need to give symbols for this operation. And I emphasize the symbols. They are just symbols. And I will give you examples right now. So the signature of an algebra means I give you the symbols of every operation, and I tell you what is the arity of each symbol, right? So let's see some examples. So groups, here I have a binary operation. So usually two array operation, we call them binary. And here we have a one array operation, which we also usually say unary operation. And here we have a zero arity operation, which is just a distinguished element. So this is like the identity element. And this is just the inverse map of a group. And this is the multiplication of a group. So the signature is G. To determine it, I determine the symbol for multiplication, which I denote by dot. I determine the symbol for inverse, which I denote by this symbol. I determine the element of the identity. So I just determine the symbols. At this moment, none of these have any meaning. They are not functions. They are just a symbol for a function. So actually, when I write this, it is somehow a mistake to write this here. I just wrote it for explanation, but it is not there. It is not a map. It is just a symbol. It's just a symbol with a data of a number. So a signature, formally speaking, is just a list of symbols and a natural number associated to each symbol telling me what is the arity of this symbol. Later on, we will turn these symbols into actual maps, but it will be important to keep these two structures apart, to have a symbol in one hand and the interpretation of this symbol as an actual operation as a different thing, okay? Nice. So rings as well form a very nice example. So here we have a binary operation, actually symbols for binary operations. I write this only for clarification. So here we have a binary operation plus a binary operation multiplication, a unary operation minus. So this is just take A to goes it to send it to minus A. here we have a zero arity element operation, or a fixed element, or a distinguished element 0, and the same for 1. So this is my signature for rings. And here is my signature for Lie algebra. So again, I have a 2 arity symbol plus, I have a bracket, which is also have arity 2, and I have a distinguished element of arity 0, of course. So these are 3 common, very important signatures. Is there any questions at this point? Because the next example will be a bit involved, so I just want to ensure that no questions arise
Fawzy,
for this one. Yeah,
Fawzy, could you say, or maybe I just a little more on arity? What is that?
the arity.
Yes.
The arity is just the number of inputs of the operation. So if you go back here,
Yeah.
so I defined an operation to be a map from a product of the set n times to the set itself. And this number of times is just the arity. So you think
Okay.
of this operation to taking some inputs from a set A, and the number of inputs is the arity. So
Okay.
two array operation is just the same thing as saying binary operation. So it takes 2 inputs. But the whole point is it has to be from the same set and to produce an element in the same set. That's the whole point. So for example, I'm not allowing something like R cross Q goes to R. I'm not allowing this.
Yeah.
Both of them has to be R. This is okay.
Yeah. Okay.
Yes?
Yeah.
Okay. And this is very important to keep in mind for the next example of vector space, because recall, for vector spaces, we have a set, we have addition, we have a scalar multiplication, and we have a 0. And we have a bunch of axioms here that I recall in case you need a reminder, but I more or less assume honestly that you have seen the notion of a vector space before. But here you see we encounter this problem. We have a scalar multiplication, and we have 2 sets. In general, they will be different. V will not be R. So we have 2 different sets, and we have a multiplication from this product to V. So it is not an operation in the sense I gave. And therefore, to the first impression, you wouldn't view a vector space as a kind of an algebra in the sense of universal algebra. You wouldn't believe it is an algebra. So the problem is precisely this multiplication map, or the scalar multiplication map. It is not an operation. But just to show you the flexibility of universal algebra thinking, I will tell you how to actually view vector space as an algebra in the universal algebra sense. Okay, so the idea is we will turn this operation here into an infinite number of multiplications. And each of these will be an operation of the kind we love. So let me be more precise. So for every real number, we will add a symbol. So a unary operation may be simple. I should write this symbol. This is a unary operation symbol. So, oops. So simple. Yeah. Okay. So the symbol I will, so for every real number alpha, I associate this symbol, which is supposed to be a symbol for a unary operation, and view this, just this is again explanation here, that this will be a map from V to V, and you should think of it as taking an element, a vector V, and send it to alpha dot V. So now I just say the multiplication by alpha. I consider symbols for multiplication by alpha operation. So M alpha is a symbol. Just again, I emphasize, I know I'm being repetitive here, but that's on purpose. It is a symbol. And that's why I put this V here, because this V say now I give this an interpretation, and I will come to this later. But if I didn't try, if I erase this V here, I have to erase this because it's just a symbol. To bring it into life, into existence, from a symbol to an actual map, I have to put this symbol here, this V here. Okay, but now just for the syntactic story, we have a symbol M alpha, which we think as multiplication by alpha. And now the signature of vector spaces will be the following. So we will have a unique distinguished element, so zero arity operation. one symbol for this, which we denote by 0, we will have an infinite number of unary operation symbols. So for every real number, we will have a symbol m alpha, and we will have one binary operation symbol. This tells you, first of all, that the operation symbols can be infinite. In this case, they are uncountably infinitely many. So they are not finite. So when I said we have a signature of an algebra, I never said it should be finite set, right? And here in this example, we actually allow it to be infinite, and that's okay. Universal algebra is okay. So universal algebra is okay with having an infinite number of operations as long as each of them is of finite parity. And that flexibility is huge, trust me. And if you want to formulate the axioms of vector spaces in this language, which we will see also later, this will be the axiom. So you will say, okay, I have this is an abelian group. I have that this M alpha is additive map in this sense here. And I have that they satisfy these operations, these two axioms here. So they turn multiplication into composition. They are compatible with addition. And these are the axioms now. And you see that these axioms here, if you write them down, are precisely the axioms I wrote here, right? So by this methodology or transformation rules, I turn a vector space into an algebra in the sense of universal algebra. So, and we have seen rings and sorry, we have also seen groups, rings, and the algebras. And for for the people who give the example of a K algebra is a vector space. And therefore, using this trick, we can view a K algebra as an algebra in the sense of universal algebra. So you see now we have a notion which specializes to groups, specializes to rings, specializes to vector spaces, specializes to K algebras in the standard sense, specializes even to modules. So most of the algebraic structures that were mentioned are examples of this notion of an algebra from universal algebra. This is how flexible this is. Okay? Now we want to study these algebras. That's the whole point of universal algebra. So we need some notions. So usually we start with, this is a very important notion, the notion of similarity, but we start with two algebras, and we will call them similar, or we will call them to be of the same type if they have the same signatures. This means they have the same operation symbols. That's why I was emphasizing all over the place that this is a symbol. For example, when we have a group, when I define a group, we usually say we have a multiplication map, which we will denote by, let's say, a cross or a dot or something. I give a symbol for this operation. But the dot in itself doesn't mean a specific multiplication map for a specific group. So when I define a group is, usually we write something like this. A group is a set G plus some multiplication map, so like this. This is a symbol for the multiplication map. It is not the multiplication map of I don't know of Q star. It is not the multiplication map of GL2 of R. It's just a symbol for a generic one, and that's why we call it a symbol. And that's what I mean here. So two algebras will be similar if they have the same list of symbols. And again, I will give examples. So according to this similarity type or this type, we can classify algebras into groups, rings, vector spaces, and many others. Okay. And now I have used this notation actually before when I talked about the signature here. So the signature is S. When I write 0 or 1 or 2, I mean those elements of S of arity 0 or of arity 1 of arity 2. So this just tells me which symbols are of arity 2. Okay. So this is the notation here. So Sn, if S is the signature, Sn will precisely be the n-array operation symbols on the algebra of the same type. And here the point is that they are in arity. And again, you see, I emphasize that this is a symbol in red. I know I'm being insanely repetitive about it, but it is one crucial thing to keep in mind. Okay, so when I say an S algebra means an algebra of signature S. So when I tell you this is an S algebra, it means It's an algebra, so it's a set with some operations, and I tell you what are the symbols for this operation and what are the arity of each symbol. So I give you this as a list of data. Okay. So now here we give a life to the symbols. So if we have an S algebra, again, this means an algebra with a list of symbols for the operations, and I take one operation, let's say it's an in-array operation. This is an algebra A. I write this f to power A, okay, to be the actual map, the actual interpretation. And this will be now an actual map from an M product of A to A. So again, for the case of groups, we usually write this dot is a binary operation like this as a symbol. But when I have a specific groups, let's say, what is your favorite example of group? Let's say S4. This is my favorite example of a group, right? Now I will write this as multiplication, and I will write here in the above S4. It indicates that this is now how this is the realization of the map. Is what is the actual map now? It is this. But the dot itself is a symbol for a generic multiplication on a generic group. When I want to specify it for a specific group, I have to write this symbol above. Okay, so we call this the interpretation of the symbol or the realization of the symbol. And as an example, we have seen that this is part of the signature of a group, and E is the identity element, a symbol for the identity element, and then the interpretation in Z in integers is just the zero number, 0, and then the interpretation in Q star is the number 1, and the realization in GL2R is just the identity matrix, right? Okay, so this is the difference between a symbol and interpretation, and please keep this in mind because it will play more and more role. Okay, so if we now I define you the most important notion, maybe is the notion of a homomorphism, and maybe here I should write is homomorphism. So here we start with two algebras, A and B. They are similar, so they are of the same type, meaning they have the same operation symbols. And I call this a homomorphism if this map is compatible with the realization of the operation. So what does this mean here? So this is of course the definition, but let me comment a bit on it. So we start with n elements, a1 up to an, and f itself is an n-array operation symbol, so it should take n many inputs, So its realization now is a function, an actual function. So if a is a map from a times a times a n times goes to a, so and I feed it these inputs, I get an element. This everything here is an element in A. I take the image of this according to this map. I get something, and I claim that this is the same as the other way to do this. So I take the image of every element. I actually think this is a mistake here. So this should be 5A1, 5A2 to 5AN. So maybe I should write the condition here again. Sorry for this confusion. But it is the same notion of homomorphism from groups, rings, and so on. So this is the condition, the correct way to put the condition. So in some sense, what it says is that phi commutes with the operation. So if A is now an operation of my algebra, and I want this map to commute with these operations, right? So if you write this definition for the case of groups, you get the notion of a group homomorphism. If you write it for rings, you get a ring homomorphism. If you write it for Boolean algebras, you get a Boolean algebra homomorphism. If you write it for vector spaces, you get a vector space homomorphism, which is just a linear transformation that you are familiar with, and so on and so forth. Okay? So I think there is a question. If we relax this distributive law in this algebra, can we create a non-commutative algebra that perfectly I don't see how this is related. I'm also not sure what you mean by quantum superposition in an algebraic sense. Because quantum superposition in mathematics, it just means that your operations are linear. So, but anyway, maybe we'll discuss this near the end. Okay, so the notion of a super algebra means that we have a subset, and we require the inclusion map to be a homomorphism. This is what we mean when we say that something is a subalgebra. Another question: how are FA and FB related in the definition of homomorphism? Okay, so recall that FA is a map from A times A times A to A, and similarly for FB. So FB here will be a map from B times B times B goes to A. So maybe let me draw a diagram for you. What was the name? Rizwanullah. Okay. Rizwanullah, let me write you a diagram. So here is the diagram. I think it will explain it. So maybe let's take n equals 3. So A times A times A goes to A. This is FA. And here we have B times B times B. This is FB. And here we have a map phi from A to B. And here we have a map phi cross phi cross phi. And by this, I mean it takes A1, A2, A3 to phi A1, phi of A2, phi of A3. Okay? And I would like the condition that this is a homomorphism just mean that this diagram is commutative. Meaning that if I go this direction, so I go first FA and then phi, this is the same as going phi times phi times phi, and then composing all of this with FB. So this is the relation between FA and FB, that it satisfies this condition. Or visually, that this diagram is commutative. So to go this direction is the same as going this direction. Or symbolically, it means that this operation, FA, commutes with the map phi, and which is just written here. So these are 3 different ways to say what this means. I hope this makes it a little bit more digestible. Is it more transparent to you, Tuanullah, now? I hope.
Rizwan, you can unmute yourself.
Yes, please unmute yourself.
Yeah, thank you so much for the explanation. But I was actually worried that maybe there are many options for FA and FB. Or I'm mistaken here?
No, so when I write this symbol, I mean I fixed the meaning. So this is not any function. Oh, this is actually a good point. When I write if A, it is not, I'm not saying any function, I'm fixing the function. That's the whole point. That's what is the difference between a symbol and its realization. Its realization is an assignment. So for every symbol, I assign a function which I denote if A. So now I fixed the function if A. So when I say an S algebra, S is a signature, so a list of symbols. And when I say an S algebra, it means I have a set A. I have an assignment for every function symbol if I assign a fixed function if A of this form, right? Think of a group again. So a group, I have these symbols, multiplication minus this operation, and I have an identity element. The realization would be a set G will be a function like this. So now we go back to the function and an inverse map like this, and an element, fixed element of G. So this will be the realization. So I fix everything. I fix the set. I tell you what is the set. I tell you what are, now I should put actually this G here to ensure that it is actually the realization. So this is just a set and an interpretation of the symbols into an actual map. So these are now fixed. They are not arbitrary anymore. Once I put this upper script, it is no longer arbitrary. It is a fixed meaning. Okay?
I see.
So when I go to the definition of a homomorphism, now everything is fixed. This is fixed. This is fixed. So it's actually a condition on the map phi or phi.
I
Is
see.
it okay?
Perfect. Thank you so much. Yeah.
Yeah, you're welcome. And please interrupt me. There is no point of going over because everything will be built on the previous notion. So please feel free to interrupt me. Okay. So our agenda for today is as follows. I told you a bit about the central notion of universal algebra. So I would like to tell you two things, how to use it to unify analogies and also to explain differences. For unifying analogies, I will give you the example of quotients and the first isomorphism theorem. And for explaining the differences, I will talk to you about the Birkhoff variety theorem. Okay, so this is the agenda for the rest of this talk. So let's talk about quotients. So usually, and ignore the slide for a second. Usually, when we do quotients in groups, we have the notion of a normal subgroup, which allows us to quotient. In rings, we have the notion of an ideal, and we use an ideal to quotient. So people will usually write things like a group G quotient by N, or a ring R quotient by an ideal I, or something like this. So we would like objects which allows us to do the quotient. And they are normal groups for groups. They are ideals for rings. And you can ask, okay, for a general algebra, what are the correct notion which allows us to construct such quotients, right? And the answer is that of a congruence relation. And I will first of all tell you what is a congruence relation, and then tell you how it relates to normal subgroups and ideals. So a congruence relation on an algebra, so again, we fix an algebra. So a congruence relation on an algebra is just an equivalence relation. So I assume you know what is an equivalence relation. So it is in particular a subset of A cross A. So it's a subset like this. And I denote this congruence relation by the symbol tilde. So it is a subset of A cross A. And it should be compatible with the operation. That's why we call it congruence. So this means the following. So if we have a list of elements A1 up to AN and B1 up to BN, such that A1 is equivalent to B1 and A2 is equivalent to B2 and so on. So every two elements corresponding elements are equivalent, then the evaluation of these functions are the same. So the evaluation of the functions of these realization functions don't see the difference between equivalent elements. That's why we say it is compatible with the operations. Because if the evaluation of the functions on equivalent elements are equivalent to maybe I actually this is also again a typo. I should write here equivalence. Okay. So to give you an example that you are familiar with, think of something like your algebra is integers as, let's say, as a ring, right? And you have your operation is the operation of modular mod n, right? So you will write something like A congruent to, so the congruence relation, A equivalent to B mod n, something like this. And you will see, for example, that addition and multiplication are compatible with this operation. So this will mean in this case that if I is congruent to B mod n, this will imply that, for example, A1 plus A2 is congruent to B1 plus B2 mod n. So I suppose that you have seen, all of you, this theorem before. And this is also why the terminology comes from, the notion of a congruence. So this is usually called the congruence relation, and that's why we call this as a congruence relation. So this is the notion of a congruence relation. It is actually quite intuitive. It is just an equivalence relation which is compatible with the algebraic operations. Of course, we always have, if we take just A cross A, this is like the maximal congruence relation. And if we take only the pairs A comma A, it is also a congruence relation. And as another example, if we take an abelian group and we take, first of all, a subgroup H. So H is a subgroup of G. And we define an operation, a relation where G is equivalent to H if and only if the difference of them lies in H. Then this will also be a congruence relation. Congruence relation. Okay? Okay, so now having a congruence relation, we can always form the quotient. And the quotient will be just the set of equivalence classes under this equivalence relation. And now here is a one instance where it is important to keep track of these symbols. So here I want to tell you how to interpret this as an algebra. So I need to tell you what is this map, what is the interpretation of f inside this object. And it will be given as follows. So first of all, it takes inputs a set of equivalence classes, and I need to give you an equivalence class. So here are the brackets. So what I do is I take an element of every equivalent class. So A1 here, AN here. I evaluate F according to A. So this is now an element in A, and I take the class of this. So I want to take the evaluation of F in a classes. I take a representative of every class. I perform F on this representative inside A, and I take the class of the resulting thing. And this is well defined, meaning it doesn't depend on my choices of the representatives. You can prove this. It's a very good exercise in case you never did this. So it gives me at least an interpretation of F inside A mod tilde, which, and you can prove that this is actually now an algebra of the same type. So A quotient tilde is similar to A, meaning they have the same operation symbols, as you see from this equation. And we always have a surjective homomorphism from an algebra to its quotient by sending just A to the equivalence class of A. As examples, if we take the quotient by these pre-mentioned congruence relation, you always get just a point or you get A back. So these are kind of quotient that you always get, right? And also you know this from groups. You always can get the zero group from any group as a quotient, or you get the group from itself as a quotient. And now the question is, okay, this is the most general notion of a quotient of universal algebra, but how it relates to normal subgroups and ideals in rings. So let's take the case of groups as an example. So the whole situation is explained by this theorem. So we have G is a group, and we have a congruence relation, which we also denote tilde. And to tilde, we will associate something which I will call N tilde, which is just the equivalence class of the identity. So it is just the set of all elements G which are related to the identity, and we claim this is a normal subgroup. So to every congruence relation, I take its equivalence class of the identity, it's a normal subgroup. So this is the first part of the theorem. The second part of the theorem is, well, here I take the equivalent, the quotient that you learn in school, that which is take the quotient of G by a normal subgroup. Here you take the quotient that I told you about earlier, and they are the same thing. They are isomorphic as groups. So it doesn't matter whether you take the quotient by this normal subgroup that we constructed or by the congruence relation. They give you the same result as groups. But moreover, we have covered all possible quotients. So there is a bijection or a one-to-one correspondence between congruence relation of a group G and the normal subgroup of G. So in one direction, if I have a congruence relation, I told you how to construct a normal subgroup. But you can go the other way around. And the way to do this is very similar to how I defined this example here. So in this example, I did it in an abelian group, but it is more or less the same in general. So in general, let me maybe write it. So in general, if you have a normal subgroup here, I associate tilde n, which is an equivalence relation, actually a congruence relation, and it is defined as follows. So G is equivalent to H if and only if, by definition, GH minus 1 is an element of N. This is my definition for this equivalence relation. And you can show that this is, first of all, an equivalence relation. And this is also a congruence relation. So this will give you a map in the other direction of sending N to tilde N. And you can show that these two maps are inverse to each other. So you go this as the identity, or you do it the other way, it's also the identity. So we have a bijection between normal subgroups and congruence relation. Okay, you can do the same thing with ideals and with rings, and you will find in the case of rings that we have a one-to-one correspondence between congruence relations and between ideals. That somehow tells you that the congruence relation notion is the generalization of both. and it is actually way more. And as I will tell you in a moment. So let's now see the first isomorphism theorem. So here we have two similar algebras, so they have the same operation in symbols, and we have a homomorphism, which you know by now what it means. So first of all, I construct this kernel, and this kernel, remember, in this general setup, it is not a subset of A. It is actually a subset of A cross A, and its definition is I take the set of all ordered pairs A comma B such that the image of phi on the first component is the same as the image of phi on the second component. So phi of A equals phi of B. And I call this the kernel. And the claim is that this is actually a congruence relation. So we can take the quotient by this congruence relation. So I can form A mod kernel phi. And I claim that the map which takes this equivalence, this class, to the image phi of A is well defined and is injective. So here I take a map and induced. So we start with this phi from A to B. I define this phi tilde, which is an induced map from the quotient by the kernel into B. And I define it the usual way. I take an equivalence class. I take a representative. I evaluate phi of this representative. And I land in B. Okay. And then this diagram is also commutative. So meaning that if I go this way is the same as going this way. So said differently, any homomorphism of algebras can be factorized into something which is surjective and something which is injective. So this is the first isomorphism theorem in universal algebra. And guess what? It generalizes every isomorphism theorem you have ever seen in your life. So the first isomorphism theorem of groups is a special case of rings, of Boolean algebras, or vector spaces, of modules, you name it. As we discussed, all of these are examples of algebras in universal algebra. And this first isomorphism theorem, you apply it in each of these cases. It gives you the usual first isomorphism theorem that you are familiar with. And in that sense, it does unify everything. Because usually when we do abstract algebra, we reprove this theorem several times. We do it once for groups. In the next semester, we do it once for rings. We do it in linear algebra again. Those who do modules do it again, and you do it 4 times in your life. Life is more interesting to do the same proofs 4 times, seriously. So you do it once for universal algebra and you go sleep, you can use it for the rest of your time. Okay, so this is an example of this unification power. But now, this is not just a unification. It is even more powerful than any of these. So, and let me explain here. So usually when we have, let's say, groups, we have a map like this, and we usually define the kernel as the pre-image of some distinguished element. For example, for groups, it is the distinguished element of the identity. And if we are in rings, it is a distinguished element of the zero, the additive entity, and so on. But the problem would be if you have an algebraic structure which doesn't have any distinguished element. How would you define the kernel in this sense? You can't, because there is no distinguished element. And this kind of algebraic structure do appear. For example, the theory of semigroups, which means a set with a multiplication map, which is just associative, is an algebraic structure with no distinguished element. So you cannot define kernels this way. It is impossible. So you have to go to the realm of universal algebra and use this notion of a congruence relation. That's, by the way, the only way to do it. So for groups and rings, it was optional. You can do quotient by congruence relations or by normal subgroups. Here, it is a must. It is unavoidable. For other examples, for example, something called heaps, also there are no distinguished. And these heaps are actually very important structure. So you might not have heard of it before, probably, but it is very important. And you can think of a heap as a group where we forget the identity element, whatever this means. It has a very precise mathematical meaning, but I am not going to talk about this. I put this here just to intrigue you and catch your curiosity to Google this after the talk, because it's an interesting rabbit hole. In any case, for heaps as well, you will need this notion of a congruence relation to actually define a quotient. So in many algebraic contexts, we cannot use similar notions as normal subgroups or ideals. We have to use congruence relation. And that's also the power of universal algebra. It doesn't just unify, but it actually gives you methods to study more general and harder examples that would be very hard to deal with otherwise. Okay, now I fulfilled my promise about the unifying analogies part. Now let me tell you a bit about universal algebra and how it explains the differences. And by the way, I want to know how much time do I have. We also started a bit late, right?
Yeah, it's okay. It's okay. You can finish it on your time, so that's okay.
Okay. So before I do this, let me tell you a bit more about the difference between a property and a structure. And to explain this, I will present the notion of a group, the definition of a group, in two different ways. So let's start the usual ways that you see in school. So a group, according to many teachers, is